Techniques for computing limits, Introduction. There are three ways to find a limit. One way is to graph the function. Even though f is not defined at 3, we can still describe the behavior of f as x gets closer and closer to the target point 3. Since f approaches 4 as x approaches 3, we conclude that the limit of f as x approaches 3 is equal to 4. Another way to find a limit is to make a table of the values of the function. Since f approaches 64 as x approaches 1 from the right, we conclude that the limit of f as x approaches 1 from the right is equal to 64. The third and most reliable way is analysis. Analysis is what we want to do today. Recall that sometimes the function evaluation at a is the same as the limit at a. Sometimes the function evaluation at a is not the same as the limit at a. There are certain functions that I call nice functions, where we are guaranteed that the limit is equal to the evaluation. It is good to know which functions are nice. Why is that? If you know that a function f has the property that its limit is equal to its evaluation, then to find the limit you need only evaluate the function. So let's study our nice functions. Functions for which the limit is equal to the evaluation. Polynomials. Rationals, as long as your denominator doesn't equal 0. If your target point means that your denominator will be 0, then you cannot do this evaluation. You've got to do something else. Trig functions. If you stay in the domain, if your target point is not in the domain of your trig function, you cannot do this evaluation. If it is in the domain, then all you need to do is evaluate. Alright, these are your basic nice functions. From this, we're going to build more nice functions. Suppose that the limit of f is equal to L. Here's what you know. The limit of 5 times f is equal to 5 times the limit. The limit of f to the 6th is equal to the limit to the 6th. The limit of the odd root of f is equal to the odd root of the limit. The limit of the even root of f is equal to the even root of the limit. Let's see how this plays out. Suppose we would like to find this limit. We first determine whether 2 pi over 3 is in the domain of tangent x, and if it is, we want to determine the value of tangent of 2 pi over 3. 2 pi over 3 is in the second quadrant. I want to remind you that the first number of the ordered pair is the cosine, and the second number is the sine. I also want to remind you that tangent equals sine over cosine. So look at the ordered pair, and we want to take the second number and divide it by the first number. So tangent of 2 pi over 3 is equal to negative radical 3. So 2 pi over 3 is in the domain of tangent, and in fact we know its value. Tangent of 2 pi over 3 is equal to negative radical 3. That tells us that the limit of tangent exists as x gets closer and closer to 2 pi over 3. Since we know the limit exists, we can use the rule that the limit of the root is the root of the limit. So we go ahead and do the evaluation. The limit of the root is the root of the limit. The limit is equal to negative radical 3, and the third root of that is what we find. And I just used the fact that the square root of 3 is 3 to the 1/2 power. And I get negative 3 to the 1/6. Here I'm making the claim, I'm doing a new problem. Here I'm making the claim that the limit of the root is equal to the root of the limit. All right, so I just made a whole lot of assumptions. The first assumption that I made is that 5 pi over 3 is in the domain of secant, and in fact it is. Secant of 5 pi over 3 can be determined. The other assumption that I made is that secant of 5 pi over 3 is in the domain of a radical function, i.e. that secant of 5 pi over 3 is positive. And in fact it is. Secant of 5 pi over 3 is positive. So to do this limit, I had to determine that 5 pi over 3 is in the domain of secant. I also had to determine that secant of pi over 3 is actually positive. All right, so let's go ahead and do the evaluation. I want to remind you that secant is 1 over cosine. I also want to remind you where 5 pi over 3 is. Look at the first of the ordered pair, so cosine of 5 pi over 3 is equal to 1/2, and I substitute that in, and then flip, and my final answer is radical 2. All right, more ways to build nice functions. As x approaches a, suppose f is going to L and g is going to m. Different functions, same target point. The target point x going to a. If you know this, if you know that both of the limits exist, and you have to know that both limits exist, then you know a bunch of different things. You know that the limit of the sum is the sum of the limits. You know that the limit of the difference is the difference of the limits. You know that the limit of the product is the product of the limits. And you know that the limit of the quotient is the quotient of the limits, assuming that your denominator is not going to 0. Your denominator can't go to 0. If it does, you can't do this. You've got to find another way to find the limit. All right, so what I'd like to do is an example. So here I'm making the claim that the limit of the difference is equal to the difference of the limits. Why is that? Well, that's because the two limits exist. How do I know the two limits exist? In the first limit, 4x squared, that's a polynomial. Polynomials are nice functions. In the second limit, cosecant, cosecant is nice as long as I stay in the domain of cosecant. And pi over 3 is in the domain of cosecant. So all I have to do is go ahead and find the limits. On the third line, I remind you that cosecant is equal to 1 over sine. All right, so what is sine of pi over 3? We locate pi over 3 and we look at the second of the ordered pair. So sine of pi over 3 is radical 3 over 2. And instead of sine of pi over 3, I put in radical 3 over 2. And then I need to flip that fraction. Dividing by radical 3 over 2 means multiplying by 2 over radical 3. And then last thing I need to do is rationalize the denominator, which is my last step. If you have any questions, let me know. This is only an introduction. There's more to this section, but this will at least help you get started. Take care and have a great day.